Chemical reactions can be really fast or really slow, as this time-lapse video showed the reaction of the displacement of silver from copper. In AS, we looked at the main factors that affected how fast a chemical reaction could go, or the rate of chemical reaction. And he found out it was dependent on temperature, concentration, pressure and surface area, and also catalyst. For A level, we're going to look at how we can measure reaction rates. Also going to look at how we can look at a reaction rate by varying concentrations of reactants and deriving rate equations or rate expressions. In a second video, we'll be looking at how we can use these rate equations to deduce reaction mechanisms. In this experiment, we're going to look at how changing the concentration of reactants affects how fast a chemical reaction takes place. First of all, we look at iodine here. Iodine is a brown solution, and when we mix it with propanone over a period of time, the colour of the iodine changes from this brown colour to colourless. One method might simply be to mix the iodine and propanone together and record the time taken for the mixture to become colourless.
Reactants were mixed together and the stop clock started simultaneously. In the following 4 sequences, the video has been speeded up by 6 times to make the changes easier to see. Try to estimate in each case to the nearest 10 seconds when the colour of the iodine just disappears.
Clearly, to look at the effect of changing, for example, the concentration of the propanone, you'd have to repeat this experiment a few times, varying the concentration of propanone. So let's look at a more efficient method. A more efficient way to monitor the rate is to use an instrument called a colorimeter. The colorimeter will measure the change in absorbance of light passing through the iodine solution over a period of time as it changes from brown to colourless. The colorimeter that we use in college is the Mistrica colorimeter. The samples are placed in these little containers here, which we call cuvettes. The cuvettes are uniform in dimension, so they're usually 1 centimetre by 1 centimetre, and the light passes through the solution, and as it passes through, if the solution is colourless like water, no light will get absorbed. However, if the light is coloured, like in iodine, some of the light passing through will be absorbed and will be shown on the display on the colorimeter. This, in fact, is a slight oversimplification, and we'll be investigating colorimetry in more detail when we come to look at transition metals. And we'll be investigating something called the Beer-Lambert law. But for now, we'll leave it as that. The instrument we tend to use at college is a Mistrica colorimeter. It's the simplest to use. So the first thing to do is to select the colour of light that is going to be passing through your solution. There are 3 LEDs, red, green and blue. And what you want to do is choose light that is going to be absorbed by the iodine solution. It's mainly reflecting in the red, so it's possibly best to choose the green LED. First, we need to calibrate the apparatus, so we insert a blank, which is usually water, because that is absorbing no light. And we need to then calibrate the instrument. Instruments always need to be calibrated because they fluctuate. So we set it to 0, because 0 light is being absorbed by the cuvette containing water. Then you put your sample containing the iodine and propanone, and you allow it to record as the colour disappears, as the colour changes. You allow the reading to drop and monitor that over a period of time. There were 3 separate investigations carried out in which the concentration of iodine was reduced from 4% to 3% to 2%. On the y-axis we have absorbance, and on the x-axis we have time. Notice that absorbance has no units. So you can see over time, as time goes on, the absorbance drops as the amount of iodine in the reaction mixture reduces. Experiment was then repeated with a greater concentration of iodine, as you can see here, because we've got greater absorbance because we've got more iodine in there. And again, as the concentration of iodine runs out, as it gets smaller and smaller and smaller, the absorbance drops. And we then carry it out with a higher concentration of iodine, 4% iodine, and again, because we've got a higher concentration of iodine, the absorbance is greater. And again, the experiment is allowed to run until the colour of the iodine runs out. Clearly, what can be seen is that we can now measure the rate of reaction, because rate is defined as, quite simply, the change in the concentration of the reactant or the product over time. So here we've got a change in the concentration of the iodine. It's getting smaller and smaller and smaller, divided by time. So in chemistry we use square brackets for concentration in moles per dm cubed, so the change in concentration of iodine over time. If we then measure the gradient for each of the 3 experiments, that will give us the rate. And even just looking at those graphs, you can see that the gradient is exactly the same, which tells us no matter if you increase the concentration of the iodine, the gradient remains the same, which tells us that changing the concentration of the iodine is having no effect on the rate. Another series of experiments were carried out in which the concentration of the iodine and acid were kept the same, but this time the concentration of the propanone was changed. So the concentration of propanone went from 2.5% and then doubled to 5%, and then increased to 7.5% and then to 10%. So here the concentration of propanone had gone up 4 times. If we now calculate the gradients for each of these 4 experiments, that will give us the rate for the change of concentration of propanone, and take the data, we can then plot another graph of rate versus concentration. Just to remind you again how to work out rate when given this data, you get the rate by dividing the change in concentration. So that's the concentration at the end here, which is roughly 1.15, and the change in the concentration here, which is 0.6, and the change in time, which is here, which is roughly 160, and we've gone from 0. So this is this triangle here. So again, don't forget how to measure the gradient. So here I've calculated the change in absorbance to be about 0.55. The time, which is, because our triangle starts from here to here, that's 160 take away 0. So that comes out in the change in absorbance of 3.44 times 10 to the minus 3. So we do the same, we measure the gradient, so you can see on these lines, by drawing the biggest triangle possible to calculate the gradient to those curves, the initial rates. So if we take the tangents to each of these curves, calculate the gradient for each one, and then plot a second graph of the rate of change in absorbance per second on this axis here versus the increase in the concentration of propanone, this time as a percent here, we get a straight line graph. And from this graph we can deduce that the rate of change with respect to the concentration of propanone is directly proportional. So here is a table of the concentration of propanone and the rate. And it can be clearly seen, even looking at this data, as you double the concentration of propanone from 2.5 to 5, the rate doubles. As you double the concentration of propanone from 5% to 10%, 7.7 times by 2 is 1.54 times 10 to the minus 2. The rate also doubles. It's much easier to see this in a graph. So plotting a graph of our data, the concentration of propanone on the x-axis, this is the independent variable, this is the one we've changed, and this is the rate that's dependent on it on the y-axis, you can see that as you double the concentration of propanone, the rate also doubles. So we get a straight line graph showing that the concentration of the propanone is directly proportional to the rate of reaction. The gradient of this graph here is the rate divided by the concentration of propanone, and that's a constant value, and we'll give that value the symbol lowercase k. So we can now derive what is called a rate expression, and we can say that the rate for this reaction is this constant k times the concentration of propanone. Let's now compare this to the first experiment where we varied the concentration of iodine. If we plotted a graph of rate versus the concentration of iodine, our graph would look like this. As the gradient doesn't change, no matter how much you increase the concentration of iodine, from 2 to 3 to 4%, the gradient is always the same, the rate doesn't change, we can therefore deduce that the rate does not vary with the concentration of iodine. So when you divide the rate by the concentration of iodine, you get a constant value, which it doesn't change. And what we say is, in this case, the rate is equal to the concentration of iodine to the power 0, because anything to the power 0 is 1. The rate is not vectored by the concentration of iodine. However, in the case of the propanone, we can say that the rate is proportional to the concentration of propanone to the power 1. Let's now have a look at what happens when we vary the concentration of the acid. Again, a series of reactions are carried out. This time, the concentration of iodine and the concentration of propanone are kept the same. All that is varied is the concentration of the acid. So here is a series of 5 experiments where the concentration of the acid or the hydrogen ion has been varied. So what we're now going to do with these results is plot a graph of concentration of the hydrogen ions on the x-axis, because that's the independent variable, and the rate on the y-axis, the dependent variable. Again, a straight line is observed, and from this graph we can deduce that the rate on the y-axis is directly proportional to the concentration of the hydrogen ions on the x-axis. If we take the gradient of this graph, where that is the rate divided by the concentration of the hydrogen ions, we will get another constant. Substituting this back into the equation, we can now come up with a rate expression which tells us how the rate changes when we vary the concentration of hydrogen ions. And because it's directly proportional, the rate is proportional to the concentration of hydrogen ions to the power 1. In this section, we're going to look at the rate expression. The rate expression, or rate equation, looks at the contribution of all of the species that affect the rate of the chemical reaction. These include the reactants and maybe catalysts too. So now we're able to derive a rate equation for the investigation. So remember, the chemical equation for the reaction that's taking place is propanone was reacting with iodine and hydrogen ions or acid reacting as a catalyst. So the rate equation is always written in the form of the rate and the concentrations of the reactants raised to these powers, and these are called the orders of reaction. And the definition of order of reaction is the power to which the concentration of a reactant is raised in the rate equation. It's also important to note that the rate equation is also known as the rate expression. And the rate expression can only be derived from carrying out experiments. It can't be predicted by looking at the overall stoichiometric or balanced equation like you can for Kc, the equilibrium constant. Lots of students get these confused. You can only derive rate equations or rate expressions from experimental evidence. Now we can't find this until we've actually done the experiment. So let's look at our experimental data again. We found that when we plotted a graph of the concentration of propanone versus the rate, we got a straight line, and therefore it's directly proportional, and therefore the order of reaction with respect to the concentration of propanone is 1. We say that x equals 1 And we say that the reaction is first order with respect to the concentration of propanone. So WRT is with respect to. Again, when we varied the concentration of hydrogen ions, we found we also got a straight line. It was directly proportional, and therefore the power with respect to the concentration of hydrogen ions is 1, and therefore we can now say that Y equals 1. Or we can say it's first order with respect to WRT, the concentration of hydrogen ions. Thank you. When the experiment was repeated with changing the concentration of iodine, there was absolutely no effect on the rate, and therefore we can describe the order with respect to the concentration of iodine as 0. We found that the rate was equal to the concentration of iodine to the power 0, and therefore we can say that Z equals 0, and therefore we can now say that the reaction is 0 order with respect to the concentration of iodine. So we can now write a rate expression, and we can simplify it. So here are the orders of reaction with respect to each of the 3 reactants, and since the concentration of hydrogen with respect to the concentration of hydrogen is 0 order, anything to the power of 0 is 1. So we can now leave it out of the rate expression. The overall order of the reaction is the sum of the powers. So the overall order of the reaction is 1 plus 1, which equals 2. So we say that the reaction is second order overall. Now this will tell us a lot about the mechanism, and we'll investigate that later. If we now look at the rate expression for this particular reaction, we've not explained what this lowercase k is. K is known as the rate constant or velocity constant, and the only factor that will affect the value of K is temperature, and we'll be looking more closely at K when we see how K and temperature are related. What we've not explained so far is what is this constant with the value with the symbol lowercase k. This is called the rate constant or the velocity constant. And we're going to look at now how we can calculate values for it for a particular experiment, and how we can look at how to calculate units. So in this experiment we've got 2 reactants, C and D. The order of reaction with respect to C is second order and first order with respect to the concentration of D. So what we need to do is to look at the data for experiment 4 to find out a value for the rate constant K at a particular temperature, because remember K is affected by temperature. So we need to find a value and also deduce the units for this particular experiment. First thing you need to do is to rearrange the rate equation. So we have here our rate equation, and we need to isolate K to get K on its own. So we need to take the concentrations of C and D and divide both sides by the concentrations of C and D to isolate K and get K on its own. Make sure you can rearrange simple rate equations. So now we have isolated K, and it's the rate divided by the concentration of C squared and the concentration of D from experiment 4. Here is the data from experiment 4. You now need to put that into your calculator, but don't forget to square the value for the concentration of C because it's second order, and that comes out at 57. We still haven't given units, however, so what we need to do now is to look at units in the data for experiment 4. The units for concentration, for rate, are moles per dm cubed per second, and the units for concentration are moles per dm cubed. So you simply substitute these back into the rate equation. On the top, on the numerator, we've got the units for rate, and then on the denominator, we've got units for concentration. And we can cancel through straight away. But then it still looks a little bit untidy. So what we need to do now is we need to expand the brackets for the moles per dm cubed squared. It becomes moles squared dm to the minus 6. Again, that's still untidy. We'd like to tidy that up. So we bring these to the top, and moles to the minus 2 become moles squared becomes moles to the minus 2. dm to the minus 6 becomes dm to the plus 6. Seconds to the minus 1. We're going to do some exam practice from your independent study booklet. So the first question talks about propanone and iodine reacting in acidic conditions as described in the experiment using the colorimetry. So in this experiment it says give the overall order for this reaction. So that's quite simple because it's first order with respect to the concentration of propanone, first order with respect to the concentration of iodine. So the answer to that is quite simple, it's second order. So now we're given some experimental data and we're going to find a value for the rate constant for the reaction. Again, we've been given experimental data, and because it's first order with respect to both of them, we simply need to rearrange this rate equation to get K on its own. The first step, rearrange the rate equation to get K on its own. So hopefully you should be able to rearrange simple equations, and therefore we divide the rate equation on this side by the concentration of propanone and hydrogen ions, and therefore we need to divide the rate also by the concentration of propanone and hydrogen ions. So make sure you tell the examiner, you show them the rearranged equation. Don't, whatever you do, just dive and put your numbers in there, because you will get credit for rearranging the equation as it's given. What you then need to do is simply substitute in the values for the concentration of propanone and the concentration of hydrogen ions. We can ignore the concentration of iodine because it's zero order and doesn't appear in the rate equation. So once you've input the rate, which is 1.24 times 10 to the minus 4, the concentration of propanone and the concentration of hydrogen ions, you come out with 3.44 times 10 to the minus 5. Please be mindful of sig figs. And the smallest number of significant figures is 3. So the answer is 3.44 times 10 to the minus 5. Now, to get the units, we simply put the units into the rate expression here, and the units for rate. So here's the units for K. The units for rate, as we can see here, are moles per dm cubed per second. So that goes onto the numerator, moles per dm cubed per second. And on the denominator, we have got the two concentrations, and that's moles per dm cubed times moles per dm cubed. Now this cancels out straight through, and we're left with the units for K as this. That looks untidy, so we now bring moles, some plus 1 to the top, and that becomes moles to the minus 1. dm to the minus 3 becomes dm to the plus 3, and seconds to minus 1 stays as it is. The final part of the question asks us to deduce the initial rate changes, and students find this difficult, but all it is again is substituting into the rate equation. So deduce how the initial rate changes when the concentration of iodine is doubled, but the concentration of propanone and hydrochloric acid are unchanged. And the answer is it's going to be unaffected. The initial rate of reaction is not affected because iodine, the concentration of iodine does not appear in the rate equation. So the initial rate of reaction, absolutely no change. What we will now do is look at some exam questions where we're asked to deduce a rate equation and deduce a value for the rate constant giving its units. So in this particular question here, we're given two theoretical reactants, A and B, and the initial rate. And the experiment has been repeated 3 times. And what we're trying to do is to deduce a rate expression, and that's the rate equation. It's the same thing. And also to deduce a rate constant. So our general rate expression is always of the form of the rate constant followed by the concentration of reactant A to the power x, where x is the order of reaction with respect to the concentration of B, multiplied by the concentration of B raised to the power y, where y is the order of reaction with respect to the concentration of B. If we now look at 2 experiments where the concentration of B remains unchanged, but the concentration of A has been tripled, we can then compare the rate in experiment 1 and experiment 2 to see how the rate has been impacted. So we can ignore the effect of B because the concentration has not changed. And what we can see is that if we increase the concentration of A 3 times, let's look at how we calculate how the rate had increased. So here the rate is 1.89 times 10 to the minus 3. I've changed that to 18.9 times 10 to the minus 2, divided by the rate here, which is 2.1 times 10 to the minus 4. The 10 to the minus 4's cancel. 18.9 divided by 2.1 is 9. As the concentration of A is tripled, the rate goes up 9-fold. So since the concentration of A to the power x and the concentration of A is increased 3 times to the power x, the rate has gone up 9 times. Therefore 3 to the power x equals 9. It therefore follows that x equals 2. So the order with respect to the concentration of A is 2. It's second order. To find the order of reaction with respect to the concentration of B, we haven't been given an option of where the concentration of A has been kept the same. However, what we do know is the order with respect to the concentration of A. So let's look here where the concentration of B has been doubled and the concentration of A has gone down by a half. And we'll now look at the effect on the rate. So we're going to compare experiments 3 and 2 to find the order of reaction with respect to the concentration of B. In order to find the order of reaction with respect to the concentration of B, we need to choose 2 experiments where B has been varied. Unfortunately, there are no experiments where the concentration of A has been kept constant. However, we do know the order of reaction with respect to the concentration of A. So let's choose experiments 3 and 2. In experiment 3 to 2, the concentration of A has been halved. And we know that the concentration of A, the order with respect to the concentration of A, is second order. Between experiments 3 and 2, the concentration of B has been doubled. But we don't know the order of reaction with respect to B. That's what we're trying to find, so we'll put that as Y. And now the rate change between experiments 3 and experiments 2 is 1.89 times 10 to the minus 3 in experiment 2, where the concentration of B has been doubled, and 3.78 times 10 to the minus 3. So to find the rate change, let's cancel out these before we dive for our calculators. And that comes out to a half. The rate has gone down by a half. We know that a half squared is 4. That's the concentration of A that's been changed by a half to the power 2, times by the concentration of 2 to the power y, where y is the order of reaction. And therefore, if we now take this over to the other side, that equals a half times by 4 over 1, which now comes out as 2. 2 to the power y equals 2, and therefore y is equal to 1. It's first order with respect to the concentration of B. We now have our rate expression, and now we need to find the value and the units for our rate constant K. So as we looked in the last part of the video, we need to rearrange this equation to isolate K on its own, and that involves dividing both sides by the concentration of A and B. And now therefore the rate constant K is equal to the rate divided by the concentration of A squared times the concentration of B. And the rate, we can choose any of the experiments, 1, 2 or 3, because it's a constant. So if we, for example, choose experiment 1, the rate in experiment 1 is 2.1 times 10 to the minus 4. The concentration of A in experiment 1 is 0.12, but don't forget to square that because it's second order with respect to concentration of A. And the concentration of B in experiment 1 is 0.26. And again, as we saw in the last part of the video, the value of K still comes out to 57 no matter which experimental data is used, and the units come to moles squared dm to the minus 6 second to the minus 1. Often, kinetics questions will give you actual experimental data to analyse. So in this question, question 3 from your booklet, you were given butadiene dimerizing, given this equation here. Now, even if you know nothing about the molecules and the reactions, that doesn't matter. But it gives you a graph for the reaction as the reactants, the butadiene, dimerizes, joins together to form these one molecules plotted against time. So this is a time concentration of reactant graph. And it asks you to draw a tangent to the curve when the concentration of butadiene is 0.0120 moles, which is here. Now remember, a tangent to the curve should touch as much of the curve as possible with your point being in the centre. When calculating a rate and drawing a tangent to the curve, always get the biggest triangle possible. Again, this will be an approximation depending on how good your tangent is, but remember how to work out the gradient. So it's the change in concentration of butadiene over time. And the change in concentration of butadiene is here, which is roughly 0.015. Take away the start concentration, which is 0. So that's the change in concentration. And the time for that change in concentration is your time axis here, which is roughly 8,000 seconds, take away 0 because we've gone through 0. So it's the gradient of this triangle here. The units for rate, because that's moles per dm cubed, it's going to be moles per dm cubed on the top, moles per dm cubed here, and seconds here. So the units of rate are moles per dm cubed per second. In the next part of the question, it tells us that the initial rate of reaction has a value of 4.57 times 10 to the minus 6 moles per dm cubed. Use this value together with the rate obtained from your tangent with this value here to justify that the order of the reaction is 2 with respect to the concentration of butadiene. So what do we mean by the initial rate of reaction? Well, that would have been obtained had we drawn a tangent to the curve going through time 0. So let's look at the data. When time is 0, the initial rate, the concentration of our butadiene was 0.018. So that's the concentration at 0 minutes. And there's the concentration that we were asked to find the rate for. So in our first experiment here, the concentration of butadiene was 0.018. And we've now reduced the concentration to 0.012 to the power x. These are the rates. This is the initial rate here, 4.57 times 10 to the minus 6. And here's the initial rate when our concentration dropped to 0.012. So if we raise this to the power x to find out what the order is with respect to the butadiene, that comes out to 1.5 to the power x, which is the order with respect to the concentration of butadiene. And if we divide the rate for the two experiments, the rate has increased 2.43 times. And it just so happens that if you square 1.5, you get 2.43, and therefore x is equal to 2. It's second order with respect to the concentration of butadiene. This is the 8th question from your independent study booklet. And in this question, you're given, first of all, you're told that there's an ester and it was studied under alkaline conditions, so we know this to be saponification at a fixed temperature. And we're told that the rate is first order with both respect to the ester and respect to the hydroxide ions. So the first thing they want us to do is to name the ester, and then using x to represent the ester, write a rate equation for this hydrolysis. A rate equation, some students wrote a chemical equation. So first of all, let's name the ester, and then, in fact, let's do this part first. It's first order with respect to the ester and first order with respect to hydroxide ions. So we can quite simply say that the rate equation is the rate, and don't forget your rate constant, with respect to the ester. So I'll give the formula for the ester. It's HCOOCH2 CH2CH3. It's first order with respect to that, so you don't need to put the 1 in. And it's also first order with respect to the concentration of hydroxide ions. Okay, let's name the ester. The first thing you must do is to draw out the full structure of the ester. Remember, an ester comes from an alcohol, which is this part here, condensed with a carboxylic acid, which is this part here. So the name of this ester comes from the alcohol, and the stem of the alcohol is propyl because there are 3 carbons, and the stem of the carboxylic acid that it came from must be a meth, so that's going to be a propyl, and because there's 1 carbon here, it came from meth. So it came from propanol and methanoic acid, so the name of the ester is propyl methanoate. For this part of the question, all you needed to do was to substitute the words into our rearranged rate equation. So as before, if we're asked to find the rate constant, we need to rearrange the rate equation. So to isolate K, we need to divide both sides by the concentration of the 2 reactants. So here's our rearranged rate equation. We then substitute the values. Let's check the rate. The initial rate is 8.5 times 10 to the minus 5. The concentration of the ester, which I've got here, is 0.24, and the concentration of the hydroxide ions is 0.35. The maximum number of significant figures allowed here, or decimal places if we look, you can see here we have 3 sig figs, here we have 3 sig figs, but here we only have 2 decimal places. Sorry, here we only have 2 sig figs. So you could get away with saying the rate is 0.12 or 0.10 because the number of significant figures is only 1. Now let's look at the units for K. On the top is rate, and they've told us the units for rate are moles per dm cubed per second. And we've been given the units for concentration of X as moles per dm cubed, and the concentration of hydroxide ions is moles per dm cubed. That cancels out with that, that cancels out with that, and therefore there are units for K, but let's tidy it up. Moles to the plus 1, when it comes to the top, becomes moles to the minus 1. dm to the minus 3, when it comes to the top, is dm to the plus 3. Seconds to the minus 1. This next part of the question has historically been answered really badly. Let's have a look why. It says, in a second experiment, At the same temperature, because remember K is affected by temperature, water is added to the reaction so that the total volume was doubled. Now calculate the initial rate of reaction. So effectively, if you are doubling the volume of water, you are reducing the concentration of the mixture by a half. So if you have your reaction mixture here in this reaction vessel, and you're effectively doubling the volume of water, you're effectively adding twice as much water, you're diluting it, and therefore the concentration is reduced by a half. So you take the original concentration of the ester, you divide it by 2. You take the original concentration of the hydroxide ions, you divide it by 2. And now we also have the rate constant. So we substitute these values back into the rate equation, but this time to find the new rate. So the rate constant is 0.10 times by the new concentration of the ester, which is 0.024 over 2, which is now 0.012, times by the concentration of the hydroxide ions, which is 0.035 over 2, which comes out at 0.0175. So the new rate of the units we know are moles per dm cubed per second at 2.1 times 10 to the minus 5 moles per dm cubed per second. In the next